Okay, so today we are going to get started with separations and get on to part A. We are going to dive into some of the ideas surrounding the Clausius-Clapeyron equation, vapor pressure, and relative volatility, and just kind of what these mean, as well as deriving some equations. For the start of part A, we are going to look at starting from the Gibbs energy per mole for the vapor and liquid phase of a pure component to derive the Clausius-Clapeyron expression for vapor pressure. So something that we know is that the Gibbs energy in the liquid phase and vapor phase of a pure component should be equal to each other. And I'm also going to talk about why this is true, just to give some more information on that. And after that explanation, we're going to go ahead and try to get this Clausius-Clapeyron equation that you've probably seen before if you've studied chemical engineering or chemistry. And before I get too far into this, I did want to highlight with my notation, such as this G with the underbar, I use the underbar for moles, the hat for mass, and the little dot for time. So for now we're just sticking with this per mole basis to make it a little bit easier for us. And what I'm looking at in this diagram that I drew up is we have a pure component that has a vapor and liquid fraction inside of this closed container. And what we want to know right now is why does the Gibbs free energy equal in each of the phases, why is the Gibbs free energy the same? One thing we know is that the total number of moles, which I'm going to use a T for, is equal to the number of moles in the vapor phase plus the number of moles in the liquid phase. And then we can also say that the change in moles, in total moles, is 0 because this is as I said, a closed volume. We're not losing or gaining any moles in total. And then we can also say that any change in the vapor moles of this pure component should be equal to the change of the any change in the vapor phase moles of this pure component, it should be equal to the change in the moles in the liquid phase. Since this is a pure component, we can say that. And from this equation, we can say that Ng, this is going to be the total N, which I'm just going to say is N. So N times G is equal to the moles in the vapor phase times the Gibbs free energy in the vapor phase plus the moles in the liquid phase times the Gibbs free energy of the liquid phase. And as I said right here, the more correct way to write this would be the change in moles total times the Gibbs free energy total at a constant temperature and pressure is equal to 0. This right here comes from the fact that the change in the Gibbs free energy of a pure component is equal to negative S, the entropy, dt plus V dp plus the summation of, this is chemical potential, times the change in moles. So at a constant temperature and pressure, this right here goes to 0, this goes to 0, and because this is a pure component with ideal conditions, this is equal to the Gibbs free energy for this component. So we can take this equation and simplify it a little bit by saying the change in Gibbs free energy, the total Gibbs free energy, is equal to the Gibbs free energy in the vapor phase times the change in moles of the vapor phase plus, because of this summation right here, the Gibbs free energy in the liquid phase times the change in moles in the liquid phase. And this should be equal to 0 for a pure component in our scenario right here. Okay, so now that we've established that that is true, our next step is to basically say that this right here is true, that the Gibbs free energy in both of the phases is equal to each other. So I'm going to write this right here in a little bit different of a way. So the change in, we're going to do right here, the moles times the Gibbs, constant temperature and pressure, so we're using this guy right here. We're going to say that right there is equal to 0, as we had determined already. This is equal to NV, the moles in the vapor phase, times the change in Gibbs free energy in the vapor phase at a constant temperature and pressure, plus the Gibbs free energy in the vapor times dNV. Then we need to do the same thing for the liquid phase, so plus moles in the liquid phase times dGL, constant temperature and pressure, plus the Gibbs free energy in the liquid phase times the change in moles of the liquid phase. So one of our basic thermodynamic equations that we know is that the Gibbs free energy is equal to the enthalpy minus temperature times entropy. And sorry, I already forgot completely to say, up here, when we said that this is equal to 0, we just said that this equals 0, and down here we said that equals 0. So what we see from that is these are equal to each other. And one more thing that I again noticed that I mistakenly did is that the change in moles of the vapor phase is equal to the negative change in moles of the liquid phase. So if the liquid phase were to lose 5 moles of this pure component, then the vapor phase would have to gain all 5 of those moles in that phase. So here, since we know that they're equal to like the negative of each other, we'd say dNL equals negative dNV and substitute that in. And what we see is we cancel these out, leaving us with the Gibbs free energy in the vapor phase is equal to the Gibbs free energy in the liquid phase. What we're doing right here is our question from the beginning. We want to derive the Clausius-Clapeyron expression for vapor pressure, which is right here. So we're going to want to express this Gibbs free energy in some other terms. We know H, the enthalpy, is equal to the internal energy plus pressure times volume, and that is work done on the system or from the system. And then we also want to say that dH is equal to du plus, and then we have to do our multiplication derivative rule. So P dV plus V dP. Now we can plug that into there. So we can say that the change in the Gibbs free energy equals VU plus PdV plus VdP minus TdS plus SDT. Okay. That minus right here should actually carry into that SDT term. So we have the change in Gibbs free energy is equal to the change in internal energy plus the pressure times the change in volume plus the volume times the change in pressure minus the temperature times the change in entropy minus the entropy times the change in temperature. We also want to expand out this du term, and we know that du from thermodynamics, the change in internal energy of a system is equal to the temperature times the change in entropy minus the pressure times the change in volume. And we can again plug that in to here. As you can see, there's already a few terms that we can cancel out, which is kind of the goal here. So we have this negative PdV and a positive PdV, and that cancels out. And I think, yeah, we have TdS and negative TdS. So after that, we get a simplified equation of the change in Gibbs free energy should be equal to the volume times the change in pressure minus the entropy times the change in temperature. What we already established earlier with this GV equals GL, you can also write that as the change in Gibbs free energy of the vapor phase is equal to the change of the Gibbs free energy in the liquid phase. We can now write out this equation in a different way to kind of express both the vapor phase and the liquid phase. We can say that the volume in the vapor phase times the change in pressure minus the entropy in the vapor phase times the change in pressure, or temperature, sorry, is equal to that same thing, but in the liquid phase. And then to simplify this some more, we'll group our pressure and temperature terms, so we can say that the molar volume of the vapor phase minus the molar volume of the liquid phase times the change in pressure is equal to negative S L minus S V. I'll just write that as SV minus S L. I said that and then I did the opposite thing. Okay. Times the change in temperature. Our reason for doing all of this is because of this term. We know that the change in entropy of the entire system should be equal to the negative change of enthalpy of vaporization divided by the temperature of the system. Looking at our Clausius-Clapeyron equation, we can already see we have the delta HVAP and those temperature terms. Now we can write this a little differently again. And keep in mind, for a real-life situation such as this, the volume in the vapor phase would be much larger than the volume in the liquid phase, so we can approximately say this is about 0 in comparison to the vapor phase, which we are subtracting from. Since this is an ideal gas, we can use the ideal gas law. PV equals nRT. And since I have been expressing this in terms of a molar volume, I'm going to rewrite this as P V over N equals RT. This is just the molar volume. So I can say that the molar volume is equal to RT over P, R being the universal gas constant. Now that we have that, we can plug this into here. So I'm going to go ahead and do that really quick. This equation that I just wrote out is the Clausius equation, or the Clausius formula, whichever you want to call it. I'm going to, in order to get to the Clausius-Clapeyron equation, put all of the temperatures on one side and all of the pressures on one side. So we have R over P dP is equal to the change of enthalpy of vaporization. We're dividing the temperature from the left-hand side to get T squared times dt. And we are going to integrate each side. This side we're integrating from the first pressure to the second pressure. This side is from the first temperature to the second temperature. This universal gas constant is a constant, so we can pull it out. And then just rewrite this. With a P there. With a 1 over P there. This delta HVAP is also going to be a constant, going from T1 to T2, 1 over T squared times dt. And now we just need to integrate this. So we know that the integral of 1 over P is natural log, so R times the natural log of, it would be P2 minus P1, which you can also write as P2 divided by P1 due to log rules. Here we're integrating, you have a 1 over T squared, that's a T to the negative 2 power. If we're taking an integral, we need to make sure that the answer will result in this right here. So if we have a negative T to the negative 1, the derivative of that would give us that right there. I think somewhere along the way I made a mistake with this negative sign, which can also happen whether or not this is exothermic or endothermic, but this should be a negative right here. This negative would make it a positive, but I think somewhere along the way I made a mistake with that negative sign, but we should have this left side equal to negative delta HVAP 1 over T2 minus 1 over T1, which we can see up here. I wrote the well-known Clausius-Clapeyron equation, and we now have that. I'll just write it down the way I have it up there. And so that is our answer, and that is how we got there. All of those calculations were just to get to this equation right here. And so what do we want to do now is we want to start with Raoults' law for vapor-liquid equilibrium. the Clausius-Clapeyron equation that we derived above, circled in orange, in order to derive the conditions that are needed in order for the relative volatility to be constant. So actually this is not like the problem we did up here, because up here we had one pure component. Down here now we're talking about having two components. And we want these two components to have a relative volatility, which would be their saturation pressure ratio to each other. We are going to treat these two components as being in an ideal mixture, just for a simplification of our calculations. And as it said above, we want to use Raoults' law. So we have this xi pi sat is equal to yi p. Xi is the mole fraction in the liquid phase. Pi sat is the saturation pressure. Yi is the mole fraction in the vapor phase. And then P is just the system pressure. So we want to go from this for our two components in an ideal mixture. And we want to derive the conditions that are needed for this to be true. So as these values change, we still want this to be true. We'll write down our Clausius-Clapeyron equation that we derived. I'm going to call these components A and B. So this relative volatility of A and B should equal to PA sat times PB, or PA sat over PB sat, which we can also write, as I said, due to log rules, as PA minus PB sat, the saturation pressures for both of those. Now we are going to write out the Clausius-Clapeyron equation, but for each component. We're going to do this for component A. So for component A, we have the natural log of P, the saturation pressure at temperature 2 divided by saturation pressure at temperature 1 equals negative delta HVAP over R times 1 over T2 minus 1 over T1. And I will add a little a here to denote that this is for A. And then we can separate this out a little bit and say that the saturation pressure of component A at temperature 2 is equal to the pressure of A, the saturation pressure at temperature 1, minus the rest of the equation. And, sorry, that would be the natural log. The natural log of both of these. We just separated it out right there. And in the same way for component B, I'm going to go ahead and take this equation just for ease of comparing. The natural log of saturation pressure of B at T2 is also equal to the natural log of the saturation pressure of B at T1 minus the enthalpy of vaporization over the gas constant, and then our temperature ratio right there. So from up here, we said that the relative volatility between components A and B is equal to the saturation pressure of A minus the saturation pressure of B. So I'm going to go ahead and use these two as the saturation pressure of A and B. Essentially, that means I'm just going to subtract these two equations. So subtract A from B. And then we get and I'll just fast forward as I write this out. Another thing I forgot to write for these equations is their little a there and b there because the enthalpy of vaporization could be different, which we will get into that. But we have this over R, and we would end up adding this. Whoa. So we're not worried about this ratio. This should stay constant. And, sorry, rather than this 0, I should have written, I don't know why I wrote that, the relative volatility of A and B. So it's not 0. I have no idea why I just did that. This is correct. All right, so we have this written out. This should stay constant because it's just the saturation pressures of each of the components at a certain temperature. But right here we have these temperature dependent terms because we're subtracting the second temperature from the first temperature. So that will be some sort of value. And we are subtracting this, adding this. In order for this to be constant, we would require that the enthalpy of vaporization of component A be equal to the enthalpy of vaporization of component B. If this is true, then these terms would be negative some value, let's call it z, plus z, that's 0. Therefore, you're then only depending on this right here, which gives you a constant relative volatility. And I think that is it. In order to have this, we need the enthalpy of vaporization of both components to be equal. If that is satisfied, then the relative volatility will be constant. Okay, sorry for that being kind of hectic. My brain just forgot some things there, but hopefully I caught them all. Hopefully I clarified everything for you guys, and I think I did. So Part B will be coming out soon. It's focusing on some different topics, so look forward to that.